My name is Neehar Peri, and I'm excited to share with you the work which I've been doing this summer through the Robotics Institute Summer Scholars Program. Today I'd like to talk about open-world 3D detection and tracking in autonomous driving. But first I'd like to thank my collaborators Achal Dev, Dr. Deva Ramanan, and Dr. Shu Kong for their help and support. First, I'd like to start by framing the problem of open-world detection and tracking, which is commonly referred to as MOT. MOT is an essential part of the modern autonomy stack. However, existing models approach MOT by training and evaluating on a fixed set of common classes, which we call the closed world setting. Now, this closed world evaluation is great for 99% of driving scenarios, as this set of common classes often includes cars, pedestrians, and most common objects that you see on the road. However, it's the 1% of driving situations which can cause problems, and that's exactly what we want to address and try and improve. So the goal here is to create open world autonomy that's aware of a diverse set of objects. And as discussed previously, we know that these common classes in a closed world setting are so important for a majority of driving situations. So we don't want to sacrifice performance on these particular classes, but we also want to try and improve robustness to never before seen novel objects. When considering open world detection and tracking, it's also important to consider the long-tail distribution of annotated data. For example, in the nuScenes dataset, there are a significantly larger number of annotations for cars and pedestrians than there are for wheelchairs, animals, and emergency vehicles. And this imbalance makes it difficult to train individual detector regression heads on these less commonly seen categories. As a result, many datasets, including nuScenes, simply disregards these less prevalent categories and only evaluates detection and tracking on commonly seen categories. We're interested in specifically exploiting the annotated but never used in training or evaluation classes, such as emergency vehicles, strollers, personal mobility, debris, and animals, to understand how we can explore open world detection and tracking in the context of existing datasets. We start our exploration of open world MOT by establishing a simple baseline using a state-of-the-art detector and tracker method known as CenterPoint. CenterPoint is trained in the traditional closed world paradigm, meaning that it's unable to detect and track unknown objects. So in order to create a baseline for the open world, we simply threshold the output of the CenterPoint detector such that predictions below a certain confidence value are assigned to be unknown objects. And the motivation here is that low confidence detections may correspond to object categories outside of the fixed detector's vocabulary. Despite the simplicity and effectiveness of our baseline, we're interested in improving open world robustness. To this end, we propose a grouping-based method which classifies objects not by their class label, but rather by their object size. And the hypothesis here is that the inductive bias of a model trained on only closed world classes causes a model to detect open world objects of interest. Specifically, training on cars and vans can help detect things that are not previously seen, which may have the same shape and style of a car or a van. We incorporate the group-based 3D detector into our baseline by leveraging the detections generated by this group-based detector and assigning them to the unknown bucket. So from our original baseline, we have high-quality closed world detections and low-quality unknown detections. With this new group-based detector, we have a lot of mixed quality unknown detections. And in order to improve the quality of these unknown detections, we remove duplicates that correspond to the known closed world classes. So specifically, we remove duplicate bounding boxes from the unknown class such that we know that all bounding boxes in the unknown class are unique. Since we know that the closed world detector serves as an oracle in that it has very high confidence detections, we can be guaranteed that all detections that are not duplicates of these high confidence closed world detections must in fact be unique unknown detections. Now we pass these detections to a tracker as in our baseline and generate open world tracklets. Before we can talk about results, I want to define a few evaluation metrics. For detection, two important metrics are mean average translation error, which determines the difference in bounding box center between the ground truth and predicted bounding box, and mean average orientation error, which determines the difference in yaw between ground truth and predicted bounding box. As for tracking, both MOTA-RO and ID recall both determine how well a tracker is able to persistently identify these novel, unseen, open world objects. To highlight a few of our results, it's clear that the fusion-based method is able to improve upon the baseline. Specifically, for the detector, it's able to reduce translation error and orientation error by more than 50%. And the tracking algorithm is able to improve recall, both MOTA-RO and IDR, by almost 30 and 20% respectively. To conclude, I'd like to reiterate the importance of open world 3D detection and tracking in autonomous driving. It's important to realize that most benchmarks only consider 99% of the situations you may encounter in the real world. But before we're fully ready for autonomous driving, it's important to consider the edge cases, particularly how a system can interact with the open world. I'd like to take a second to thank Rachel and Dr. John Dolan for the opportunity to participate in the Robotics Institute Summer Scholars Program, and I'd like to thank you for spending some time hearing about my work.